Hello, for this video we are asked to determine the mass moment of inertia about the z-axis for this general cone. It's got a base radius of big R, a height of h, and a mass of m. So we're starting with our general formula. IZZ is going to be equal to the density of our cone times the integral over the volume of r squared dv. Alright, so the first thing we need to do is figure out this dv term. And so that's the rate at which volume is changing, and it's going to be we need to put this in terms of r as we move out from the center. So if I am some distance, small r, from the center, the rate of change of volume is going to be kind of this cylindrical area. So if I imagine distance r away, there's going to be a cylinder that's exactly r away from that z-axis. Alright, and two things are happening with this cylinder as we move away. Number one, the circumference is going to be getting bigger as we move away, but also as we move away we start with a tall, thin cylinder and it's getting shorter and shorter until it gets to a height of 0 out at the small radius is equal to this big R value. So the outside area, not including the top and bottom, is going to be dV. I'm going to multiply that by the rate at which I'm moving out from the center. That is the rate of change of my volume there. So I'm going to have the circumference times the height is the outside surface area of my piece. So the circumference is 2 pi r, and the height, I'm going to call this, rather than using h, because I've already used that term, I'm going to call this y. Times y. Alright. So I also am going to need to figure out, the dv is also going to have this dr term. So I need to figure out y in terms of other variables. Because at r equals 0, it's y is h. At r is equal to big R, my y value is going to go down to 0. And it's kind of a line in between those two. And so the equation for this line, if we think about it, we start at h. And then I've got a negative linear slope, and so I've got minus, it's going to be rise over run, and so rise is actually, negative h, over the run would be big R. And that whole thing, this is the slope times R. Alright, so let's put all of this together. So z is going to be equal to the density times the integral, and in going out from the center I'm going from 0 to this big R. I'm going to have r squared. Alright, now for dv I've got 2 pi r times h minus h over big R, little r, times dr. Alright, so I want to move everything that is a constant outside of my integral. So when I do that, IZZ, it's got density, this 2 pi is going to move out, and I have to figure out, I can also take out, there's an h and an h, so I can kind of factor out that h, and then I've got to figure out what's left inside. So 0 to big R. I'm going to have an r cubed term between this r squared and this r, and now what I'm going to have left over is 1 minus little r over big R. Alright, so that, if I multiply this r cubed, I'm going to have r cubed minus, it's going to be little r to the 4th over big R. And that whole thing gets multiplied by dr. Alright, so now we have to take the integral of this term here. And so if I take the integral there, if I do IZZ equals, and I keep all my constants out front, h. Alright, so 0 to big R. The integral of r cubed is going to be 1/4 r to the 4th. And I'm going to have minus 1/5 r to the 5th. Alright, so now I need to evaluate this from 0 to big R. And so if I plug in, I notice if I plug in 0 to both of these, it's going to be 0. So I'm just going to evaluate it, or just kind of look at it at this big R. So I'm going to have 1/4 big R to the 4th minus 1/5 big R to the 5th. Alright, so r to the 5th over r, I'm going to have both of these terms are actually going to be big R to the 4th. And so I'm going to have 1/4, basically minus 1/5, times big R to the 4th. And of course, all of this, these constants in the beginning are also carried down there. Alright, so 1/4 minus 1/5, this is actually going to be 1/20 r to the 4th. And out front, I've got rho times 2 pi times h, and that's I, z, z. Alright, so I want to simplify this a little bit, because one of the things I need to do is I need to put this in terms of my mass, m. And so mass is going to be the density, rho, times the volume. Alright, so the volume of a cone is going to be 1/3 pi times h times r squared. Alright, so if I pull out that term, so I'm going to have I z equals, I'm going to do 6 times rho times, if I need 1/3 pi h r squared, and this is my volume, times 1/20 r squared. And so this is, I've taken two r squared value pieces from this, and I multiplied, I had the original 2 in here, and so I split 2 into 6 times 1/3. 6 times 1/3 is going to give me 2. This is the volume, density times volume. This is just the mass. And so what I'm left over with is 6 times the mass times 1/20 times r squared. Alright, so 6 over 20 is going to give me 3/10. And so I z is going to be equal to 3/10 times the mass times r squared. And that is how we go about solving for the mass moment of inertia of a cone via integration. So thank you for watching, and I hope to see you again.